In this video, we're going to look at the difference between vectors and scalars and see some examples of our most frequently used vectors and scalars. Firstly, a vector is a physical quantity that has both magnitude and direction. A scalar is a physical quantity that can be represented and is only represented by a magnitude. So no direction with a scalar. A vector, we have magnitude and direction. By magnitude, we mean how much. Direction, where is it going? So an example here, vector, let's say there is some wind blowing to the northeast at 15 miles per hour. Okay, this example might be relevant for an airplane. That's my airplane. Say it is flying in some direction like north, which is where that arrow seems to be pointing, and I have this wind that is blowing to the northeast at 15 miles per hour. There's the wind. Okay, it is not just important that a pilot knows how fast the wind is blowing, but also in what direction, right? If it's blowing in the opposite direction of the plane, directly behind it, that changes maybe how much fuel is going to be consumed, how long it's going to take to arrive at a destination. If the wind is blowing in the same direction as the flight of the plane, then it gets a healthy little tailwind that helps it arrive at its destination faster. And if it's like the one I just drew, then it's off to the side somewhere, and so maybe the pilot needs to have a little bit of course correction involved in aiming the direction of the plane such that he or she ends up going in the direction they actually want to go in. So both parts are important, and missing one part completely ruins the whole situation for everybody. So we need to have both magnitude and direction indicated in a vector. So I could represent, as I did in blue, the magnitude there is 15. I have units in orange that are miles per hour, and pilot's probably going to want knots or something. And then I have the direction in green, which is northeast. We will frequently, almost entirely, see directions using positive or negative signs. If it's in a straight line, positive direction, negative direction, or once we get into two-dimensional stuff and three-dimensional stuff, we will want to use degrees. So we could say, for instance, northeast is at positive 45 degrees. By default, all degree measurements begin at the positive x-axis. So there's my wind vector. In this case, this is a particular vector called velocity, which is a measure of the change in position with respect to time. So it's how quickly something's moving in a certain direction. So it has the velocity of how fast it's moving, 15 miles per hour, and in what direction? Well, northeast, positive 45 degrees, or whatever it is. And it happens to have the units, and our standard units are meters per second. Okay, a scalar example would be something like mass, which has just a value that I've drawn in blue with number signs, pound symbols, and a unit, like the kilogram, which is the unit for mass. We made that distinction already in a previous video. Mass has no direction, it's simply an amount of matter. A counterexample would be the vector of weight, or the weight vector, which is actually a force. Because weight is a force, it actually has a magnitude, how much, and a direction. So if these two people are standing on the surface of a planet, such as the Earth, their weight has some value that is dependent upon how much mass they have, and it has a direction, which is, when we get to gravitation, will be easier to understand, but it's directed towards the center of the Earth. So that's where the direction of that weight vector is. So your force of weight, it actually changes depending on wherever you're standing or wherever you move, because you're actually changing the direction. It's still pointing towards the center of the Earth, but because you can see with those two people, from our perspective, their vectors are different. The units for that weight vector, for instance, another comparison is the Newton, which in a previous video we said is actually made up of fundamental units, or base units, kilogram meters divided by seconds squared, and the unit for mass is just the kilogram. So you can actually see that not only is the weight vector a value with a direction, it also has completely different units, and mass just has kilogram. So we need to keep those separate. Just as a recap, remember that the vector is a physical quantity that has both magnitude and direction, whereas the scalar has just magnitude. Alright, in this slide we're just going to compare the basic vectors and scalars that we're going to start with in kinematics this week. We will need to keep these straight throughout the year. As we use them, it will become much easier to do so, but we'll get through our just basic definitions. We'll start with the scalars first. Distance, which you've heard of before, is symbolized just by d. Its definition or formula is simply the space traversed, so total space traveled. If I run around a track and end up back at my starting point and it's a quarter-mile track, my distance traveled is a quarter mile. Straightforward, simple definition. You may have encountered distance equals rate times time, d equals rt. We won't use that formula because our stands for radius. But that's basically the relationship between distance, how fast something's moving, and time. So that's another way to think about the formula for distance. Speed, another scalar quantity, is symbolized by s, and it's distance divided by time. Time is another scalar quantity. It's symbolized by t and delta t. T just means some amount of time since a starting time. Delta t, or remember delta means difference, is elapsed time or change in time. Mass is another important scalar. We just said that one as an example on the previous slide. It's symbolized by m. It's a quantity of matter, kind of like the mole. And its actual formal definition in physics is the product of the volume and density, there, rho, the Greek letter. Or as Newton says, mass is the product of volume and density taken conjointly. And that's basically just because mass is kind of hard to measure directly. We have an opportunity here to look at our dimensional analysis again. Mass is equal to volume times density, where volume is the length dimension cubed, and density is the quotient of mass per unit volume, so that's m over L cubed, and our L cubes cancel out, and we're left with the mass dimension, which is what we should have, because it's mass. In terms of units, we have there next to our quantities in red the units, the meter for distance, meter per second for speed, second for time, and kilogram for mass. Those units have normal font when you see them, and then the symbols are in italics. Normal size letters, but in italics. So that's the way you can know the difference between the M at the bottom, standing for mass. It'll be in italics, whereas the M that is just a normal font would be standing for the meters, the unit. Let's go over and look at our vectors. Displacement's the first one we're going to look at. It's a normal symbol that we'll see is delta x, which we know is the difference between x and x naught, or some other previous x. And that x stands for position, where something is. So displacement is the change in position of an object or a particle, and it's symbolized by delta x, or the difference in the positions. Kind of older school symbol was s. People still use s sometimes, but we won't use s because it gets confusing, and delta x is really what the university physics level stuff uses. So there are a number of formula that we could use. You've seen some of them in practicing our literal equations. They're also on the AP equations sheet, and these are kinematic equations that we will derive this week. But that's basically different ways you could represent or find change in position or displacement. Velocity is another vector, and it is, Velocity is symbolized by v. We've seen that in some of the equations we've manipulated. It's defined as the change in position divided by change in time, or displacement divided by elapsed time. But we know we can actually rewrite that now as delta x over delta t, which is x minus x naught divided by t minus t naught. So the change in the position divided by the change in time. This is different from speed. For instance, that example of running around a track, one lap, I end up back at my starting point. So my displacement is actually 0. I've come back to where I started if I do one exact perfect lap around a track. Or if I run in a perfect circle, or oval, or whatever, I come back to the same starting point. My position has not changed. I've traveled some distance, maybe a quarter mile, but my position has not changed. Therefore, my displacement is 0. If my displacement is 0, look at my velocity equation. If my displacement is 0, my velocity is also 0. So I could have a positive distance. It must be positive if it's a distance. I go a quarter mile around a track. If I do it in 1 minute, then I have a quarter mile divided by 60 seconds is my speed. But if I look at my displacement and velocity, my displacement, like we said, is 0 because I come back to my starting point. My change in position is 0. And therefore my velocity is also 0. So it is possible to have a distance, which must be positive. You can never have a negative distance. I can therefore have a positive and negative, never a negative speed. So I can have a distance and a speed, but I can still have a 0 displacement and therefore 0 velocity. So you have to analyze the situation physically. Acceleration is the next vector that we'll encounter, and that is symbolized by a. It's the change in velocity with respect to time. So how quickly you are changing your velocity. That doesn't necessarily mean speeding up, right? It could be slowing down, because that's a change in your velocity. Pressing down on the accelerator in a car speeds you up, good for you, but pressing on the brake also slows you down. That's also an acceleration. Speeding up is an acceleration, slowing down is an acceleration. Those are changes in the magnitude of the velocity, how fast you're moving. But also, there's one more way in a car that you can easily change your velocity, and that's by turning the steering wheel. You change your direction, you are accelerating. Okay, so your speed could be the same. You could be going at a constant speed in a car, but you're turning that steering wheel, and that actually changes the direction of your velocity, and your direction changing means your vector is changing. So acceleration can also just mean change in direction of your velocity. Last one we'll mention is force. Okay, that's symbolized by F, and usually we have a little subscript there for the F, so it could be like F sub G. So that would be force of gravity or gravitation. I could also have F sub F maybe to symbolize the force of friction. Or I could just have something like F sub net, which means total, or all of the forces added together. So maybe I have F sub G acting on an object, I have a frictional force acting on an object. F sub net would mean, well, all of those added up. And we'll see how to do that. But that's just kind of how force is symbolized generally. As far as it's defined, you're surely going to remember Newton's second law, F equals ma from physical science. Even more basically, force is just defined as a push or a pull. Again, the units over there are in red. Okay, so you can see how those units, some of them, same units for these vectors and corresponding scalars, like displacement and distance, but they are still completely different things. On the center column, the symbol, we have vector symbols are in bold instead of italics, or instead of just thin regular width lettering, they're bold and they have arrows over them, which symbolize, the arrow symbolizes the direction. So as you can see, I've gone back and written arrows over everything except for just the plain X's by themselves, because that just indicates a specific position, like 5 meters from the starting point. It's only a vector once it's a change in position, so delta X gets the arrow. But I've gone through and put arrows over everything, and you can probably tell how that's going to quickly become a pain to constantly write arrows over everything. So we say formally, it needs to be a bold letter with an arrow over it, but usually we end up dropping the arrow for convenience in writing it all. So we'll end up dropping the arrows and just writing it, but it's a good practice if you get stuck or something doesn't seem right or you made a mistake. Go back through your equations and you can write those arrows over it. Think about which ones are scalars and vectors, and maybe that can help you figure out maybe where you went wrong if something happened. That's it for vectors and scalars. We'll see how we can combine them and add them and stuff in the next video. But this is the basic rundown. We need to know these. We need to know the difference between displacement and distance so we don't run into simple, trivial troubles of dealing with these quantities. These are the basic ones we'll need for the first semester. We'll come up with other ones. We'll see other ones that are derived from these, but this is the basics. Know them well.